Good evening, Dr. Ramasubbu. Let us wait for a couple of more minutes to allow other people to join. Thanks.
Sir, Sourav sir.
Hi, Dr. Ramasubbu.
Sir, good evening, sir. Sir, I
Good
am
evening.
having one small request, sir. Sir, after the problem solving session, kindly post the video in the website, sir, our class URL, sir, so that we can, if it is not possible to come during the problem solving session, means we can see it later.
Dr. Ramasubu, the videos are uploaded to YouTube. I think the links are shared with you by the NPTEL team.
Okay, what is the YouTube address, sir?
So I have a YouTube channel. It's with my name only, but the NPTEL team is supposed to share the links with you guys.
Okay, sir. Okay, okay.
Yeah. Could you please check with them once because I have been uploading my videos to YouTube regularly. They will be able to help.
Okay. In the name of Sourav, sir. Sourav. Right?
Yes, Dr. Ramasubu, Sourav Goswami.
Okay, 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 sir. Okay. Thank you, thank you.
Thanks. We'll wait just for 2 or 3 more minutes and then we'll start. Hi, good evening, everyone. Welcome to week 7 of the live sessions for ME112 Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate at IIT Bombay. I am working in the broad area of additive manufacturing. Most of the participants are regulars. Still, I'll just go over our agenda once again. We'll start with a brief recapitulation of the concepts that were covered in this week. This is all the more important because I noticed many questions in your assignments are theoretical or conceptual questions, which are derived directly from the slides. Then we'll have a problem solving session, which are more nuanced or which will help clear your concepts better. And I hope they will help you in solving your assignments. Again, for communicating during this session, please do not unmute directly. Please raise your hand, and I will call out your name and unmute you and ask you to speak. Once we are done conversing, please mute yourself again. Thank you. Let us get started. This week, primarily, the contents that were covered included the wire additive manufacturing processes. And the first slide dealt with the most well-known or most commonly encountered wire AM process, which is FDM, fused deposition modeling, or FFF, which is fused filament fabrication. Again, the classification based on the various subsystem levels uh, introduces new technologies to us. And for FDM, the material which is used is polymers or composites, and the material flow is continuous. The other sort of material flow is drop on demand, where you drop the build material or the support material drop wise in the intended regions. It will have serial kinematics. Since we are using only the polymer or composite material as the feedstock, resistance heating is sufficient. As typically we would need the temperatures around say 240 or 250 degrees Celsius only, which can be easily achieved by resistance heating. And in most cases, the supports are also water dissolvable. So even though it will involve a mechanical post-processing step where we manually remove all the support structures or most of the support structures using some tools, the rest can be removed easily by some water dissolution process. And just like every other AM process, the AM cycle is still the same. We start with the creation of a CAD model, which gets converted to an STL file for the case of indirect slicing. If you, sorry, for the case of indirect slicing. And if you want a direct slicing step, we simply skip the STL part. We orient the file, generate the supports, and then start slicing. We'll also encounter a process where this slicing is not really layer-wise but segment-wise, but that comes later. Then we plan the toolpath and generate the G codes. Often we have to deposit certain buffer layers on our build platform before we can actually start depositing our main part. So often these buffer layers are in the form of raft or brim or skirt. Then once the main and support materials are deposited, the supports are removed and the surface is finally finished. Now for any FDM type process or any FDM type machine, you'll always encounter these three subsystems or set of components. The first would actually be the filament feeding mechanism, which would consist of the pinch rollers and the build material coming out from the loop. The second would be the material liquefying or material heating zone, where resistance heating is used to actually melt the material into a liquid or a semi-solid state. And finally, through the so this is your 3, 2, and 1. Finally, through the relative motion between the deposition head and your substrate or the pre-built layers, we are successful in finally depositing our part. And as we have been discussing, so typically the feedstocks will be some thermoplastic polymers such as PLA or even nylon is used or PVC is used. And the diameter are typically 1.5 to 3 mm. And this wire is actually fed from a coil. So for say desk jet printers, they might even be in the form of a loose coil. And the filament is actually fed or pushed through the use of some pinch roller mechanisms, which are these. So one of these might be an idler, and the other might be a drive gear, and these might be joined through a spring. And the driving gear at least is connected to the stepper motor, and the stepper motor, through precise control of the extrusion, feeds the exact amount of or the exact volume of filament which is required for printing the part. Often the roller materials are hypalon or polyurethane when we are using FDM. For other wire-based AM processes such as in DED, the materials are made of metals and alloys such as case hardened steel. Now, since the filament is passed through between the rollers, an increased surface area of contact which actually help in better gripping and better control or precise extrusion of the filament material. And to increase this surface area of contact, often the grooves or toothed surface are created into both the gears. And just like with every other process, even here the pressure should be optimum, so you can't go increasing linearly. So yeah, so your pressure should be somewhere in the middle. so that there is sufficient grip. So if I am left on this point, I will have slippage because of insufficient grip. And if I'm right, maybe I'll crush the wire because of excessive loading. So we will have to maintain some moderate load, and often this is indicated. So you see this bolt here. So often this will have some markings on it. Say if this is the side view of the bolt. So it will have certain markings on it. And the manufacturer often specifies that say you have to go up to this third mark or this 3.5. So maybe there will be some other smaller ticks here as well, which actually gives us the optimum tightness or the optimum torque that we have to apply. If the pressure is too much, we'll often observe tooth marks on the filament, and they may also get crushed. Now, the slides involved several derivations which we'll not go over in much detail, but yeah, we'll definitely touch on them. So, for a given layer thickness and bead width and the traverse speed C, we can calculate the volumetric flow rate. And this flow rate can also be calculated from the amount of material that we're extruding from the rollers themselves. And equating them would yield certain useful results. In these calculations, we use something called KF, which is actually a friction factor, to account for excess or less than optimal friction conditions. And qualitatively, if KF is greater than 1, then we are applying too much force. If KF is less than 1, there is ample chances of slipping. So the amount of material extruded cannot be controlled properly, and it may be less or more than you need. Some further calculations to actually determine the force which is actually needed to push the filament through the melting region. In this case, two forces will act. One is a tensile force, which is actually coming from the spool. So this material would actually be coming out from some spool, and we would need to pull it from the spool. And if we see on the cross section of the wire, it will actually be under tension from that spool side. And because we are forcing this wire into the melting region, on the other end, F2 is a compressive force. F1 is often ignored for these calculations as compared to F2, its magnitude is very small. Also, we saw that often even loose coils may be used, in which case there is no tension at all. And it is actually the compression on the liquefier side for the feed rollers which places a limit on Q. Q is the volumetric flow rate. And once this critical limit is exceeded, feedstock filament may buckle, just like any structural member. This buckling will lead to a discontinuity in the flow or jamming, and your print will get interrupted. Also, the machine might get jammed, or for too much pressure, you might also end up damaging the rollers if your feedstock material is hard. And calculation of this buckling load is based on Euler's model, and it has been found that assuming both ends to be pin-pin joints actually yields a close enough correlation, and thus based on the assumption of both ends being pinned, the buckling load can be calculated as pi square EI by L square with the effective length equal to the length of the filament itself. Here also, we also multiply another correction factor as the cross section of the liquefier and wire are different. So when we are inserting it into the liquefier, so this distance right here, say if it is DL, where L signifies the liquefier, it will be slightly greater than the diameter of the filament, but only slightly, not too much. Again, once inside the liquefier or inside the melting region, the cross section does not remain uniform and it takes on more of this converging shape where for a certain length L1 you have a constant diameter D1, then the diameter decreases linearly, and after a point you have a constant diameter D2 at the exit for a length L2. Based on the dimensions D1, D2, L1, L2, and the angle beta, other considerations such as the temperature change in the region are accounted for. Often these derivations have assumed the conditions to be isothermal, that is, the same temperature is maintained all across the liquefier. So maybe all across the three regions, the same temperature is maintained. This might work for the steady state, but if there is an unsteady state, in the sense that if suddenly the velocity of the wire which is being fed gets increased suddenly, we know that inside this region, the wire temperature, say it is T liquefier, and here we have the temperature of the filament. So we know that because of the heating of the coils, resistance coils present all around, TL will of course be greater than TF. But if we have a sudden increase in the volume of TF bearing filament actually being pushed into this region, the equilibrium of this region will get disturbed. And the average temperature over the bulk may decrease below TL, and this will change our calculations. So we need some sort of a closed loop feedback system to account for this increase in the feeding rate or the volume flow rate. Say suddenly I want to deposit at a faster speed, or there is a region where I can actually deposit quickly because of a low requirement for geometrical accuracy. In such a region, I would actually like to deposit with a very high deposition rate, which can be achieved by increasing the feeding velocity. But then the heating in the resistance coils has also to be compensated for proportionately to be able to maintain the build quality. And these dynamics are pretty complex. Only some simplified models are available. Now, since the melted filament adheres to a liquefier or diverges, the materials undergo some shear information. And the inherent nature of thermoplastic materials is to actually exhibit shear thinning. That is, when we increase the amount of shear or the shear rate acting on the filament material, its viscosity decreases. So with increasing shear, it become more and more flowable. And a power law can be used to approximate the material behavior in this case. And this power law is used in conjunction with the assumption of a generic Newtonian fluid. These are the relevant characteristic curves of different types of fluids. So pseudoplastics, the Newtonian, which has a linear relationship between the shear stress and shear rate. Dilatant and Bingham plastic and Bingham pseudoplastics. All of this we have studied in some basic fluid mechanics courses. Now, using these power law and the momentum flux balance, we can actually determine the change in pressure in each of the three regions and then combine them to find the total change in pressure across the liquefier. This can be back substituted to obtain the amount of compressive force needed to feed the filament into the liquefier. And as I was saying, so the fluid is often assumed to be in an isothermal state and at a temperature T, which is equal to the temperature of deposition or the melting temperature, sometimes a little above the melting temperature also. However, certain changes in the flow rate may actually change this isothermal condition, and the steady state is disturbed. The average velocity of the fluid increases and the average temperature drops. If we suddenly introduce a significant volume of cooler filament, and in order to compensate for that, the heat flow rate must also be proportionately increased. Of course, there will be some lag in actually transmitting this information to the control system. And so for a short time, there will be some disturbance and perturbations will be introduced. Maybe your print quality can also be disturbed. But these days, with advances in control system technology, this lag time has been reduced significantly. There are some other derivations. And even from our calculations and the formula that were derived, can we observe that when a sudden change in the flow rate occurs, the average temperature T drops and the velocity V increases. Thus, the increase for the pressure drop. So the pressure drop also increases. When the pressure drop is increased, to counter this, the compressive force that I'm applying on the filament at the entry to the liquefier has also to be compensated for, and it will increase. Similarly, the motor power and the RPM can be calculated. Here is a quick numerical which uses all the formula derived, so I'm not touching on it again. As you saw, the buckling length or the critical length has been computed from the buckling calculations based on Euler's formula or Euler's model. So this was all about certain subsystems of the FDM process. Primarily, the three we encountered were the feeding mechanism and the liquefying mechanism. The third subsystem which we will be talking about is actually the one which induces relative motion between the substrate and the deposition head, or the pre-built layers and the deposition head, and which is actually responsible for depositing and printing the part. And some certain phenomena associated with it, such as the dye swelling phenomena and bead cooling, bead deposition spreading and bonding, also bead ironing, and surface roughness calculations for an FDM printed part. We'll also look at some of the other popular wire-based AM processes which use either polymer or composite as the feedstock material. This is the architecture, we have already looked at it. Now, it would be obvious that inside the nozzle, the polymer melt is under a stress because of the compressive forces from this side, which is continuously feeding the filament into the liquefier. And when it is finally getting extruded from the nozzle, from the tip of the nozzle, the melt is no longer constrained, and the stresses that were acting on the melt in the nozzle are relaxed. This leads to a release of the elastically stored energy, and the size of the deposited bead, or the critical diameter of the deposited bead, increases beyond the uh, nozzle diameter. So there is seen to be a swelling in this case. So here D3, which we see, is the diameter of the swelled bead, and D2 is the diameter of the exit at the nozzle. D3 is greater than D2, but not by a large extent. So usually by, say, D3 by D2 would have a ratio of 1.05 to 1.3. It can also be less. We'll read about that. And quantitatively, it is determined by the ratio of, yeah, D3 by D2 only. If it is greater than 1, of course, we can say that the bead has swelled after exiting the nozzle. If it is less than 1, we can say that the bead has shrunk after exiting the nozzle. And if it is equal to 1, which is rarely the case, we'll see that there is no change in the cross section or in the diameter of the bead. Of course, this value of the swelling ratio will often depend on the material properties and also the geometry of the extrusion nozzle. So based on the type of geometry you have, whether it is flat, uh, parallel or converging or diverging, or the length of this extrusion channel, the swelling ratio may change. And usually for such thermoplastics, it would be in the range of 1.05 to 1.3. Certain other types of filament material which are used, such as the ceramic particles or even carbon fibers, tend to reduce dye swelling. And in this case, the value of swelling may be close to 1 or sometimes even marginally less than 1. Now, once the molten filament material actually leaves or exits the nozzle, it will get deposited on the substrate or the pre-built layer. And if the flow through the print nozzle in region 3 is modeled as simple, again, positive flow, so again, assumptions here. The volumetric flow rate can be easily determined by established formulations. And again, the cross-section area can also be determined from the mass conservation and from the flow rate considerations. So your flow rate is simply the area of the cross-section times the velocity with which it is flowing. If I know the flow rate from my calculations covered in the previous slide, where I know at what rate I'm actually sending the filament material into the molten region, into the liquefying region, I already know the volume flow rate. I know the speed at which, or the velocity with which my deposition head is traversing. So I can easily calculate the cross-sectional area. Again, depending on the speed with which our deposition head is traversing, our deposition characteristics are bound to change. So one might naively assume that if I increase the deposition speed too much, without adequately also compensating the volumetric flow rate or other things, even the temperature or the heat flow into the resistance coils, my deposition rate would improve. But this is not the case because if the print head velocity is very large or sufficiently large, the bead will inherently become unstable and discontinuous. So there would be regions where it is printed and then regions of discontinuity. There would not be a continuous print. So these would be voids. As the speed is increased, the bead area is reduced, and above a certain speed, which would be achieved at minimum cross-sectional bead area, the bead will simply tear and produce gaps in the final part. Now, the maximum achievable area at the maximum head speed is similar geometry too. So we have taken inspiration from a fluid mechanics problem where the problem can be said to be analogous, not exactly the same, but analogous to an axisymmetric liquid bridge, which is stable up to a height limit. That height limit is of the order of the square of the tip height above the surface divided by pi. So this one right here. We have taken analogy from that axisymmetric liquid bridge problem, and we say that the minimum cross section of the molten bead at which it will still remain stable and will produce continuous deposited tracks without any gaps or voids can be estimated as h square by pi, h being the standoff distance. Or the distance between the nozzle and the substrate, or the nozzle and the pre-built layer, as the case may be. And here we have certain representative cases. So for right direction to the page, so the actually the head is traversing into the plane. So this is the direction of VT into the slide, and we see that for a representative head speed of 1, the area is equal to the area of the cross section of the deposition nozzle. If I decrease the head speed or the traversal speed, keeping the other factors constant, the cross-sectional area of the deposited bead will increase to twice. This is to maintain the mass conservation or the continuity equation. Similarly, if I increase the head speed to twice the original value, it is expected that the cross-sectional area of my deposited bead will simply become half. Thus, it is possible to actually modulate or control the cross-section of the deposited track by controlling the head speed, but we have to be careful not to exceed the critical values. Again, the critical velocity can also be calculated, and we can place a limit that this velocity should be less than pi squared d2 by 2 times 4 del p by a delta L 2 h square. And from the equation, it might appear that the liquid properties are not directly involved in the stability limit, but the impact of achieving the stability limit and the ability of the material to neck down from AB to the critical value, which is AB min, is affected by some of the inherent properties or the commonly known flow numbers, such as the Weber number and the Reynolds number. So I'll just touch on these also. So Weber number, which is actually denoted by WE, physically it's the ratio of the drag force to the cohesion force. I'm not going into the formula or the derivation. I'm just trying to give a physical idea of what it actually means. And I mean, qualitatively, we can say that it is a measure of the relative importance of the fluid inertia compared to the surface tension. So these factors will become especially relevant if you have, say, a multi-phase flow consisting of two fluids with different surface tensions. So Weber number is mostly encountered in such situations or modeling of such cases. I will also simply write that here, so it is useful in cases where there is an interface between two different fluids. especially in multi-phase flows. The Reynolds number is well known. Still, just for the sake of completion, I'll also write its physical significance. So it is simply the ratio of the inertial forces to the viscous forces. And quantitatively, we can say that for a laminar flow, the viscous forces dominate. So if the value of the viscous forces is high, the Reynolds number would be low. So our low Reynolds number implies and is implied by a laminar flow. Whereas if I have a turbulent flow where the viscous forces are not so dominant, whereas actually the inertia of motion of the fluid is the dominant mechanism for a higher Reynolds number, I will have turbulent flow, vortices, and other similar phenomena. Again, as we saw that, like usually for the general case, the deposited bead would actually have a oblong or the elliptical cross section. So our deposition is again into the plane. And if we take a cross section, we see these oblong shapes. And based on the hat spacing, so maybe the distance between the center of two neighboring tracks, based on the surface tension phenomena of these two surfaces, based on their molten state or their rate of solidification, different sorts of say inter-track porosities or even inter-track phenomena might be observed. So if they remain molten for a longer time, they may simply fuse together well. And even the top surface might actually be somewhat planar if the cohesion is poor and the tracks seem to retain their elliptical shapes. We'll have this non-planar sort of feature, which is actually undesirable and can lead to void. So if I also deposit, say, another layer, this was deposited on another layer. So this region is clearly a void. It can be called an interlayer porosity, which is actually a process-induced defect. Thus, the viscosity of the melt and the relative surface energies are dominant factors here. Also, the interaction of the deposition head tip with the bead may further influence the evolution of the shape of the printed bead. If it is in contact with the deposited track, if it irons the deposited track or say does some in situ deformation process on it, the final characteristics of the deposited bead will change. And the final width of this road, so since a single track may simply be called a road, determines the resolution that can be achieved as well as the contact area between the neighboring beads. And as we were discussing, so this rounded or oblong type shape will always lead to small voids. The strength of bond between the neighboring roads as well as between the different layers will ultimately describe or decide the overall mechanical properties of the part. In this context, the bead ironing phenomena is often used. So what happens is, rather than simply depositing the molten material on top of the substrate, we also bring the tip very close to the surface to maintain the Z accuracy of the deposited head. And we see that without bead ironing, so the melt is not deposited too far ahead of the nozzle. Whereas in the case of the downward motion or the bead ironing process, since it is now closer to the surface, some of the liquid melt is actually squeezed towards the front also. And what this actually helps us achieve is to first maintain the Z accuracy, as we see that in this case there was a distortion from the desirable layer height. So we can maintain the Z accuracy. And it also results in more stable flows and a flat road surface. Again, this phenomenon may be thought of to be similar to somewhat what we saw in the case of dye swelling. Now, say these are two adjacent tracks which were deposited, and here for this case, it is being said that the strength of the melt extrusion would be limited fundamentally by the strength of the bond between neighboring beads. And as we discussed, the bond strength will be a function of actually the energy of adhesion if both materials are the same. Say if both materials are made of the same material M1 and M1. In that case, sorry, if they are of different materials, say M1 and M2, in that case, the forces of addition would be responsible. And if they are made of the same material, then the cohesive forces would actually be the deciding factor. For polymeric materials, which are the common feedstock for FDM-like processes, the bead bonding actually occurs through a sintering process, which emerges through a viscous flow mechanism. And just like other sintering processes, even this is thermally driven. Thus, the temperature history of the rod, especially at the interface with some adjacent rod or adjacent bead, will be crucial in determining the quality of bond. So, for this, I'm not sure if this is a spherical or a circular cross section or oblong, but still, assume that one of the major axes is given to be 2A. Initially, we start with two beads deposited side by side. The cross sections have a major axis of 2A. And once centering starts, or once bonding between the two adjacent tracks starts, a neck will form. Now, this neck is simply the region which is in contact between the two. So, the common region or the common surface which is shared by the two neighboring beads. Often, this neck will have a radius y, or the neck will have a total length of 2y, which in the normal case would be less than the major axis of the original bead. If y equals a, then that is the most ideal case. In that case, we will always obtain a planar surface. But practically, it is never the case. Finally, diffusion and neck growth will occur. These polymeric chains that we see here, these random chains, these might even grow across this necking interface and will get randomly distributed. Now, further, the area and the cross section on the perimeter of this bead can be approximated through relevant formula. And in this case, the cross-sectional shape of the deposited bead can be considered to be an ellipse because of the oblong type shape. And if we were to assume a uniform temperature distribution throughout the cross-section, so in this cross-section, throughout, my temperature is uniform. It might change at different lengths along the bead. So say this is if this is closest to the extrusion tip, and my directional velocity is this. So I can estimate that if I take the temperature readings at say 3 points, it can be reasonably assumed that T1 would be greater than T2 would be greater than T3 because T1 is the most recently deposited one. It has not had as much time to cool uh, than T2 or when compared to T3. So along the length, the temperature might be different at different cross sections. But what we are assuming that at any of these points in that cross section, the temperature distribution is uniform. Thus, with such an assumption in place, the cooling process would be simplified to a one-dimensional transient heat transfer model. And also, because usually it is assumed that the mass of the base plate or the mass of the foundation is much higher compared to that of the filament. The conduction at the interface between the build plate and the deposited bead would not appreciably change the temperature of the foundation. Often, we also may artificially maintain the build plate or the substrate at a fixed temperature when we are using techniques such as preheating. So we manually ensure that the temperature does not change appreciably. But even in the case where preheating is not used, it can still be reasonably assumed that the temperature, because of conduction between the deposited filament and the build plate, for the case of FDM, will not change appreciably. This conduction heat transfer can be actually approximated in some form of convection. And with such formulation and the given boundary conditions, it has a closed form solution, which is given right here. And the closed form solution can actually be used to actually evaluate the temperatures. Now, as we have been discussing, the cross-sectional area of the bead will be inversely proportional to the velocity, and this velocity is not constant. So it changes at the start of deposition and at the end of deposition. And we have been discussing these inertia effects. Say when the print head is taking a turn, it will have to change its velocity, it will have to accelerate. So the deposition rate also does not remain constant. It varies with these changes in the build path. So please give me a minute. I'll just have a sip of water. Thank you for your patience. Yeah, as we were discussing, and based on the motion of the deposition head, the cross section that is being deposited on the substrate, so the cross section of the bead, will also change. And it is very well illustrated with this plot here. So the yellow curve right here, it actually shows the variation in the volume flow rate or the mass flow rate, whereas the red curve over here, it shows the change in the deposition velocity or the bead velocity. So at the start, we start the deposition head takes some time to actually achieve the velocity, and initially it is at rest, but we start pushing the filament into the liquefier as well as we start heating it to achieve the molten state, and thus there is some deposition which is shown here even when the print head is stationary, because the head is not moving, so it will not get deposited in one spot and may have a shape which is shown here. Of course, this is an irregular shape. Now, once the XY motion of the state of the deposition head gets activated, so initially it will accelerate to reach the desired velocity from 0 to the desired velocity, yes, so it will accelerate. Because of this acceleration, while keeping the volume flow rate or the mass flow rate of filament constant, initially there will be a decrease in the cross section of the bead or the road which is being deposited. However, once the steady state is reached and the steady printing velocity is achieved, the road would be more or less will have a uniform cross section. Of course, other process instabilities or other external factors might still introduce some fluctuations, but more or less it will be constant. Again, when the head has to take a turn or when the head is supposed to stop after depositing a track, it cannot stop instantaneously because that would lead to some infinite acceleration. So it will stop over a short duration of time. During this time, the deposition rate is or the volumetric flow rate is still constant. Thus again there will be a bulging in the cross section, and again when the deposition head velocity reaches absolute zero, there's still some time taken to actually stop the feeding of material into the liquefier, or even if the no new material is added to the liquefier, the existing material still has to be extruded out and deposited. So even at the end, some excess volume may still be deposited. And of course, it is possible to, or it is becoming possible to adjust the deposition rate with the velocity of traversal by changing the filament speed appropriately. This requires advanced control systems and control algorithms, but these are being increasingly implemented. More sophisticated systems which are coming up simultaneously adjust the filament feed rate to compensate for the change in velocity. However, as we discussed, even in this control system, there will be some lag as the information cannot be transmitted instantaneously. And this lag will actually lead to corresponding degree of under deposition, such as here, or over deposition, such as these regions over here. Now, there are also some other inherent resolution issues or lack of accuracy because of the AM model. So one, of course, we can easily think of is the approximation of the exact geometry by STL files. So it only captures or presents an approximate representation of our actual geometry. So we are introducing some approximations or errors at the pre-processing stage itself. Another source of inaccuracy can be the warpage or shrinkage of the deposited part, where warpage is occurring because of the thermal gradient in the build part. So if I'm extruding my filament after melting it at a temperature of say 240 degrees Celsius, and it is coming in contact with the print bed or the substrate, which is at room temperature, say 24 degrees Celsius, we find that the heat or the thermal gradient between the two is very large. To decrease this thermal gradient and to prevent warpage and to induce actually good adhesion between the deposited material and the build plate, we do two things. First, we apply some glue. That glue is like very basic glue, like Fevigum or something like that, with a glue stick. Second, we often heat the build plate or the substrate. So in the machine by Fractal Works, I am aware that the build plate is heated to a temperature of 60 degrees Celsius, and the deposition for material like PLA, polylactic acid, occurs at a temperature of 240 degrees Celsius. So this combination has been seen to actually result in good adhesion between the substrate and the deposited part. Again, just like any other AM like process, surface roughness is also an inherent defect, and the stair stepping effect is illustrated here. Of course, we can account for this by a post-processing operation such as a milling operation or some chemical vapor-based chemical milling or even some ultrasonic polishing-based processes. So they were mentioned here. So post-processing via mechanical abrasion, machining, or some solvent vapor smoothing is common. The surface roughness of these parts, which is induced by the stress stripping effect, or even the say the inconsistency or consistency or the perturbances in the deposition of each layer can actually be quantified using the usual surface roughness metrics such as the centerline average RA or the root mean square surface roughness which is RQ, and their mathematical formulation is given here. So RA is actually the mean variation of distance of a surface profile to the measurement center line. So the center line is actually defined for, say, I have a wavy surface. I first have to construct a line which will be such that the areas above that line say I denote them by some odd subscripts such as A1, A3, A5, and so on. And the areas below the center line highlighted in red here, and say if I address them or demarcate them by these even coefficients, so A2, A4, A6, and so on. The center line is a construction of my choice, and I will construct it such that the sum of areas above it is actually equal to the sum of areas below. So once this center line is constructed, I simply measure the distance of the asperities, which is the peaks and valleys, from the center line, take the mod, and if I call it my, integrate it over the entire sampling length. So this L here is a sampling length. It need not be necessarily equal to the length of the track or the length of the sample. It can be a subset. So usually sampling lengths are of say 8 mm, 4 mm, zero point 0.8 mm, 1.2 mm or similar. And I integrate it over the sampling length, divide by the sampling length to obtain the center line average. Another metric or another quantification of surface roughness is in the form of the root mean square surface roughness. It has the advantage that it better reflects or better accounts for some isolated surface defects as it is defined here. Again, based on these geometric considerations, modeling of the surface roughness has also been done by again assuming an elliptical cross section for the deposited bead and necessary say dilution between two beads deposited on top of each other. I'm not touching on the derivation, and these results can be readily used. A second type of wire-based EM system, which uses a polymer or composite as the filament material, has continuous material flow but is using parallel kinematics as opposed to serial is given here. So it has the advantage that because of the use of parallel kinematics, it can have a very large Z envelope. That is, it can build parts which have a significantly larger Z dimension without increasing the XY dimension. So the XY footprint or XY dimension here or XY area are still like regular or even small. Similarly, for a machine which uses hybrid kinematics, there is this other demonstration where the uh, y and z axis, so the y and the z axis are actually controlled by these parallel kinematics, and the stage only has, say, the x axis motion. So the stage can move back and forth along the x direction, whereas the y direction or movement in the perpendicular direction to x in the plane, as well as the z direction or the build direction out of the plane, are achieved by the use of this parallel kinematics. Thus, since the machine or the setup uses both parallel and serial kinematics, it can be called as hybrid kinematics based setup. And one of the very few technologies to actually use a drop on demand based material flow technique has also been discussed, where we see that so maybe in the deposition nozzle there is a plunger and molten material is present all around. And based on the need, the plunger will move along the XY direction, have an oscillatory motion about the XY direction, about the Z direction, and deposit small bits of material in one layer, then move on to the next by this rapid back and forth motion of the plunger. So as we can see inherently, this process is more vulnerable to both intra-layer defects, so defects in the same layer, as well as these intra-layer effect, or interlayer effects, that is the defects between the two successively deposited layers. However, this is still an up and coming technology. Not many processes using drop on demand techniques exist. In the third lecture for this week, we finally moved on to metal wire based AM, which is of major industrial relevance. Of course, polymer based and other materials are also important, but the commercialization aspect of AM is mostly linked to the use of metals and alloys as feedstocks. Especially the advantage with metal wire has over the metal powder is from a productivity point of view, the higher deposition rates. That is, you can build larger volumes in smaller times. Second is the handling aspect. So wires are much easier to handle, to store, whereas powders can be hazardous. They can also be explosive in certain cases. Also, in the safety aspect that they pose, or the safety risks that they pose to the operator and the user. Inhalation of powder particles can be dangerous for humans, whereas wires are safe to interact and use. Also, the cost itself of powders and wires, there's a large difference between the two. So, you to make good quality powders, you will have to resort to some atomization process such as water atomization, gas atomization, or plasma atomization. Depending on the process you use, you will have the morphology, whether desirable or undesirable, as well as the particle size distribution, and it is a costly process. Whereas for metal AM, wire-based metal AM, often the simple welding wire which is easily available is sufficient. So Professor Kapil covered some of the historical or some of the earliest reported metal wire-based AM processes through, and also pointed to the patents which give details of these technologies. So I'm not touching on them. These are interesting from a historical perspective and to show us that what insights human have had in this technology. It was invented or discovered long ago, but it is emerging right now and taking the world by storm. Even now, it is yet to be fully established or commercialized and had started long back in the 1920s. So a century has passed. Now, for metal wire based AM processes, which use arc as the heat source, maybe processes which are similar to the MIG welding or the metal inert gas welding, TIG welding or the tungsten inert gas welding or even plasma welding. And for processes which are using an energy beam as a source, such as electron beam or laser beam more commonly, are the energy beam based AM processes. Wire can be easily used with electron beam, but powder cannot. That is because powder needs some carrier gas to actually deposit it or to make it flow into the deposition chamber, whereas wire can be deposited under vacuum. Because of the use of carrier gas, the vacuum of the electron gun cannot be maintained, and thus it is not a feasible technology. Again, the support mechanisms are either not available for the case of metal wire AM processes. They have to be overcome by suitably tilting the table or using a higher degree of freedom table. Or if available in certain cases, they may be acid dissolvable, such as the case that we will cover in the slides. We'll use maybe stainless steel as the build material, as a deposition material, and we'll use copper as the support material. Copper can easily be dissolved in nitric acid, HNO3, whereas stainless steel will remain unaffected. Thus, by using this material combination, we can make support structure out of copper. Another processor which is not strictly wire-based AM, but can be said to be a predecessor or maybe a related process, is the shape deposition manufacturing. And as I was saying, it does not even use conventional slicing, be it fixed slicing or adaptive slicing. It uses something called as segmenting. What segmenting is, we will encounter in the upcoming slides. And to deposit the build material and the support material, it may use, say, two heads or two extruders. Now, it is based on the premise that the invisible surface of the model will be the visible surface of the support and vice versa. So we try to look at the model from the top. Say I'm looking at it from here. I cannot see this surface right here. So the invisible surface of the model, which is this one in this case, will actually be the visible surface of support. So if I were to make some support in the form of these long structures or even a solid support, maybe we'll just hatch it with a different color. So the invisible surface of the part or the build material is actually the invisible surface of the part is actually the visible surface of this support structure. And using this simple principle, we go on to print the parts after suitably segmenting them. Slicing is based on the visibility concepts and this principle that we just described. And the part is free from staircase effect because it has an inherent or inbuilt uh, subtractive process which is milling. So it can be end milling or face milling. So after each deposition step, the part is suitably milled to maintain the geometric accuracy. Thus, the stair stepping effect is noticeably absent. This sort of deposition creates a near net shape, and 5-axis CNC machining is used for net shaping it. Also, there's some inherent short peening or laser short peening based process to actually relieve the stresses. Many types of materials have been deposited by this shape deposition manufacturing based process. And mostly the microcasting, welding, thermal spraying, and laser welding are relevant to metals. And this microcrusting process is actually a hybridization of the MIG and the TIG based processes. So somewhere in between, neither it is a fully MIG like process nor it is fully TIG like process. And as we were saying, so primarily the materials which have been explored are the stainless steel and copper. Stainless steel for the building material, copper for the support structure. It is etched away by acid bath with nitric acid. And here the arc is established between the tungsten electrode, so like TIG, and the feedstock wire, like MIG, from a charge contact tip. The wire is actually connected to the positive terminal, whereas the tungsten electrode is connected to the negative terminal. The circuit is completed by the contact of the arc with the wire, which is being fed continuously. Because of the completion of circuit, the generated current or the current flowing generates sufficiently high temperatures to melt the material being fed, and the molten material is in a superheated stage. Why superheated? Because it is not simply sufficient to melt the deposited material alone. It is also important that the deposited molten material melts some of the previously deposited layer to induce suitable dilution or suitable bonding between the deposited layer and the previously deposited layers. And this extent of dilution, so it is something like this. This is my substrate of the previously deposited material, and this is my newly deposited material. It can be quantified in two ways. Either we can use the heights, say the height of the bead and the depth of the say remelted zone or the dilution zone, or in certain formulations, even the fraction of areas have been used. So the area of the weld bead against say, the area of the remelted zone. This dilution, so based on the process, it might change, but say anywhere between some 10 to 40% or 10 to 30%. The value of dilution is deemed important and good for the process. Important why? Because it will induce a significant or good metallurgical bonding. If the dilution is less than 10%, there is always the chance of delamination or insufficient lack of fusion between the newly deposited layer and the previously deposited layers or even the substrate. The wire then melts in the arc, forms a molten drop at the end of the wire. It will continue to build up, and when its weight overcomes the surface tension, it will simply fall on the surface and flattens upon impact. The magnetic field also helps in acceleration. In this case, the part need not be an electrode, and this is how it is similar to TIG or PO rather or plasma arc welding rather than MIG. Again, because of the large volume to surface ratio, the droplets will remain superheated in flight and contain sufficient energy to locally remelt the underlying substrate. This is important to form good metallurgical bonding to control the oxidation. Often, some inert gas is purged here, or also called shielding gas. And microcasting is often typically used for depositing stainless steel and copper-like materials. Again, the these metal wire-based AM processes may be used to deposit the materials at very high deposition rates. So if I need good accuracy, but slightly lower deposition rates, I can opt for a TIG-based metal deposition process. But if I need higher deposition rates, but with say slightly compromised accuracy or medium accuracy, I can opt for a process which is closer to MIG. Now, this is the shape deposition manufacturing that we were discussing, and we have encountered the step of segmenting. So, unlike slicing, which occurred for fixed layer thicknesses or for adaptively, when we wanted to approximate or accommodate some intricate geometrical feature, segmenting occurs only on the consideration that where the overhanging region is being introduced, or if I'm continuing with an overhang where the non-overhanging region is being introduced, or if there is any undercut feature. So if any of these conditions are encountered, we generate a slice or a segment, and we can see that the thicknesses of the segment are not uniform. So it is inherently an adaptive sort of slicing, but the algorithm is based on different factors. And in this case, we don't even do layer by layer deposition. So say even in the same segment, which is say, considered this one, it's not like we will have some layer by layer or we will deposit this entire material in one layer. We can do it in several passes. Also, we will machine it to maintain the geometrical accuracy. Another significant difference is that in certain regions, you will observe that it's not just the support material which is actually supporting the build material. Sometimes the build material is deposited before in a segment. The support material is deposited afterwards by taking help of the build material to support the overhanging regions. And then the next segment is built. So very unique sort of process. And each deposition is followed by a 5-axis machining. The slicing strategy is independent of edge approximation, where transitions between the undercut and non-undercut surfaces, or where there is change in the material composition if you are building a multi-material structure, or if there is a change in the nature of overhang, whether it is an overhanging region or a non-overhanging region. This example illustrates the concept very well. So we see that in the segment B, we first have to deposit the support material, machine it, and only then we can deposit the build material, which is in yellow here. Whereas in segment A, we find that first the build material has to be deposited, and only then the two sections of the support material can be deposited on top of it. So in a way, the build would be actually be supporting the support material. And in a segment such as C, where there are multiple components to be deposited, we have to follow an order such that each one can be deposited without disturbing the future deposition. So just like a game of Tetris, where you had these shape blocks which are dropping, and you have to deposit them such that you can so make a structure without overfilling the deposition area. So something similar to that. So we try to accommodate all of these features and try to deposit in a sequence which can actually build the part as suitable. It involves several steps. So for a typical case, it might first involve the deposition of support, then machining of the support using either a vertical milling operation or even a tilted operation by using a 5-axis CNC table. Then the deposition of the build material would be used, and that would also be machined, and so on. Another advantage that this process offers is that we can build multi-materials or FGM-like structures, or it is also possible to embed some electronic components or some information sensors within the build. This is accommodated because of the segment-wise or even inside a single segment, the component-wise deposition strategy that is adopted. So better than slicing, it is more prudent to call this process as part decomposition. We start at the bottom, and while going upward, if we see that there is any change from undercut to non-undercut region, or for the case where we are looking at the change in overhang, so regions which would require overhang will have the facets or facet normals pointing downwards. Regions which do not encounter or do not need such support structures or are not overhanging will actually have the facet normals pointing upwards. And between this transition, there will be, it can be thought that there will be some horizontal facet, which will have its outward normal exactly horizontal. So wherever the normal of the straight triangle becomes horizontal, A triangle is a prospective candidate for slicing plane. We have to identify the sequence in which the various parts can be deposited. We can use any algorithm which is suitable for us. For example, in one of his examples, Professor Kapil has used the principle that whichever component or whichever part requires or has the greatest volume, he will deposit that first. There might be multiple ways to deposit or multiple branches we can follow. There is no clear distinction. So each of them may will bring you the same result, and you can choose one based on your own defined principles. We form something called an adjacency graph and then a minimal precedence graph. It actually helps us to build the tree. So I'll just take a quick minute to explain this example. So here we had a geometry without slicing planes, which looked something like this. Yeah, maybe something like this. And it also had certain regions with supports. So this is how it looked like initially. And we identified the regions where we are supposed to segment it along or the segmenting plane or the part decomposition planes. So here we find that the non-overhang region is changing to the overhang. So one of the planes can be here. Of course, this plane can also segment the support structure. Second overhang was again, the second region was encountered here, where it was found that now this region is becoming overhanging. The third plane was here, where you have a overhang here in this region, and so on. And since these are part of the same volume, we simply combine them into one to reduce the number of parts. So as numbered here, so this is 1, 2, 3, and 4, whereas 5, 6, and 7 correspond to the support material deposition. Now in adjacency graph, what we are trying to do is simply list down all the components or all the parts which are adjacent or in contact with our seed part. So starting at part 1, that is starting at the bottom, I see that part 2, part 6, and part 5 are in contact with it, and I write them. So 5, 2, and 6. There is no preferred order between the three. I can write them in any sequence. Now, similarly, following for the others. So 2 is in contact with 5, 6, and 7. So 2 is in contact with 5, 6, there is already an arrow here, and 7. Similarly, 6 is in contact with 1 and 2, so it's already connected to 1. We put an arrow to 2. It might be connected with 7 at one point, but for this example, Professor Kapil has not considered this. So this arrow might also be present. Then we see that 5 is connected to 1, 2, 3, and 4. So we draw those arrows. So connected to 1 is already joined, 2 is already joined, 3 and 4. Moving on to the next. We encounter part 3. 3 is connected to 5 and 7. So 5 it is already joined to we write 7 and join it. And finally also to 4. 4 is also connected to 5 and 7 and the relevant arrows are shown. This is the adjacency graph. Now we want to construct the minimal precedence graph, which basically tells us that which is the least part or which is the minimum which is which I can deposit beyond which the further deposition will become impossible. So for example, here I have written 6 after 1. The reason is that if I do not deposit 6, then 2 cannot be deposited because 2 will require support in this region. If 2 is not deposited, 5 also cannot be deposited because 5 requires support here. So once I have deposited 1, my only option is to deposit part 6. Once I have deposited part 6, again, I cannot deposit part 5 directly because that will still need support. or part 7. Part 7 also needs support from part 2. So I can simply go on to part 2. So this is the path that I'm taking from 1 to 6, then 6 to 2. Once 2 is deposited, we find that both 5 and 7 can be deposited. So we can go down either route. So both of these are possible, or they may lead to the similar results. There is no advantage or disadvantage of going through one. Now, from 5, the only part left to deposit is 3. So, whereas from 2, I can either deposit 3 if I have already deposited 5, which is not the case. So, 5 is a separate route. Or if I'm not depositing 3, then the only other route is 7. So, as shown here. Once 5 is deposited, 3 can also be deposited. And once I have both 3 and 7, I can deposit 4. This is the minimal precedence graph. And then based on this graph, I can choose any one of the paths. So say a traverse along this path, and that will lead to one building deposition sequence. If I say traverse via another path, that will lead to a separate building tree or building path. So in this case, 3 paths were possible, and depending on which path you choose, the deposition of sequence of deposition is changing. It is well illustrated in this example here. And another example for drawing the adjacency graphs and the precedence graph. So again, this part, we first generated the supports which were encountered in region 4 and region 5. And then based on where the surface changed from overhanging, or the part changed from overhanging to non-overhanging, we drew a slicing plane or a decomposition plane. Similarly here, the overhang was introduced for component 3, so here is another slicing plane. And once the parts are or the components are identified, we draw the adjacency graph and the minimal precedence graph, and then go on to deposit the material. So we start with 4, then deposit 1, then 5, 2, and finally our build is completed by depositing part 3. So we see that here 5 and 2 are shown in the same level or the same horizontal level. This is because I could have gone either way. So both of these pathways are suitable. After depositing 1, I can also deposit 5. That is not a problem. Or and then go on to deposit 2 and 3. Or after 1, I can even deposit 2, then deposit 5 and 3. So it does not really make a difference. Just it'll change the sequence of deposition. So now we have recapitulated all the content that was covered. In the upcoming time, we'll solve some of the examples. So let us take a short break and resume at 8:30. So let us resume our session. The first question is related to the die swelling phenomenon, and it asks us that in an FDM process, the maximum diameter of the extruded material is 1 mm, and the diameter of the print nozzle is 0.75 mm. Then what is the swelling ratio? So just to remind ourselves, usually what happens is, say this is the diameter of the nozzle. Because of the stresses which were uh, carried by the material when it was inside, which will get released once it is extruded out. The cross section of the bead will actually swell or increase, and this can be quantified by using the swelling ratio. So if I just denote the swelling ratio by S, it will actually be equal to the maximum diameter of the swelled bead by the diameter of the nozzle. So in this case, I have that the maximum die of extruded material is 1 mm, whereas the diameter of the die opening is 0.5, 0.75 mm. So this would just be equal to 1 by 3 by 4 or 4 by 3. So 1.33 recurring. So option C is the right answer. Also see that some of the options are actually less than 1. So these may be encountered in the case of using carbon fibers or some ceramic based filaments. Now the second question describes that we have two bill filaments of different diameters. So one has a diameter of 1 mm, the other one has a diameter of 2 mm, so twice. However, the they have the same material as well as the same effective length. That is, so this question clearly talks about buckling. That even the effective length in both the cases is the same. The material is same, all the material properties such as the Young's modulus, Poisson ratio, and others would remain the same for both the two cases. Only the diameter is changing, and it is to be printed by using an FDM process. So we have to calculate the ratio of the critical forces which would be needed for uh, both the filaments. If I assume that the hinge condition exists. So again, if we just quickly recall the formula for calculating this critical buckling load using an Eulerian assumption, it was actually equal to 1.1, which is a compensation factor times pi square EDF square by 16 LF square. So DF is the diameter of the filament, LF is the effective length, E is the Young's modulus, and the factor 1.1 is actually used to accommodate the difference in the say the filament diameter as well as the uh, the entry diameter into the liquefied region, which are not the same. There is a slight difference. So this 1.1 factor is used. Now, since these properties such as the Young's modulus and others are not given, I can simply to calculate the ratio. I see that most of the things will cancel out. So if I were to calculate the critical buckling load for A versus the critical buckling load for B, I will see that all the constants will first get eliminated. Since the material is same, even the value of the Young's modulus will not come into the picture. Since the effective length is the same, even LF will get cancelled out. Only the DF will remain. So maybe I can write it as DFA square upon DFB square. Now these values are given to us. So for A it's 1, for B it's 2. They have the same units which is mm. So 1 by 4, or it can be said that yeah, PACR by PBCR or will actually be equal to zero point 0.5. So we see that the since B has a larger diameter of which is twice that of A, the critical buckling load for A will only be 1/4 times the critical buckling load for B. So just by increasing the diameter to twice the original, our second filament can actually sustain 4 times the buckling load. Thus, 0.25 is the right answer. The third question asks us, what advantages does parallel kinematics offer over serial kinematics in the context of FDM? So, serial kinematics is where each link is connected to the next via certain joints, and then the actuation of these joints and links actually creates motion. Whereas in parallel kinematics, such as we saw in certain delta type mechanisms, where the end effector, such as a deposition head, may be simultaneously linked. So they are given here as well to several links at the same time, and by the uh, actuation and parallel operation of these links, we can produce, say, even XY motion, Z motion, or even rotation and others tilting of the end effector. So, what are the advantages that such a parallel kinematic system might offer over usually encountered serial kinematic system? Will it offer greater accuracy? So, usually not, because we can tune our printing parameters to account for the accuracy. Also, there is no limitation in the sense that a serial kinematic system will not be able to reach all regions of the middle plate. It will only be restricted to a certain subset, whereas a parallel kinematic system will be able to reach greater regions or vice versa. So, accuracy in both cases can be achieved to the desired level. Can parallel kinematics offer greater build dimension or greater build envelope in the Z direction? Yes, this is possible, as we discussed. Also, while having this larger build envelope in the Z direction, the footprint in XY plane will still remain same or become even smaller. So, depending on our need, it's not necessary that to build parts of high aspect ratio or of larger volumes. We also need a larger footprint in the XY plane, and the machine has to be large overall. It can simply be slender but still accommodate a much larger build envelope. So both B and C are correct, and we say that option D is the correct option for this question. The next question is discussing the new mechanism, which is actually the drop-on-demand FDM, and it's actually asking us to ponder what are the defects or drawbacks that we can expect. So this was not touched upon in the lectures directly. Of course, the entire process was described, but if we have to think critically at what sorts of defects or what sort of drawbacks can be encountered, that's what the question is asking us. So just to do a quick recap, in a drop-on-demand type system, you had a plunger, and all around this in this region, so maybe there is molten material available, and by the up and down motion of the plunger, we deposit the material in the drop by drop fashion. So maybe small spherical drops, and we can do all sorts of area filling. So maybe start at the boundaries, and then depending on the size of the bead, the size of the geometry, or the accuracy that you want, we can even fill and adopt different strategies that were covered in our toolpath planning sessions. But what are the inherent drawbacks or the defects that we can expect? So one is clearly that there will be these voids or gaps even in the same layer. So in the conventional sense, you had this continuous bead which was getting deposited. So maybe if this is your deposition head, the material is being fed into it. So this was the, at least for the same track, there was no uh, intra-track porosity if all the build parameters were optimal. But here, even at optimal parameters, we'll see that for the same track, there will be pores between the adjacently deposited beads. I mean, there is a far greater probability of encountering pores. Also, when I'm depositing the next layer on top, so based on my deposition strategy, whether I try to deposit one on top of the other, or I try to deposit them between these gaps to in an attempt to cover them up, I will still encounter those interlayer porosities. And these are lack of fusion pores because of the lack of fusion between two adjacent drops. Again, the surface finish would be worse. And why that is because in this case at least, so for this continuous bead, the this surface. So if I'm looking from the in a three-dimensional way, so at least this surface over here would have a relatively smooth finish. And based on the deposition of the next surface, I will of course have some stair stepping. So if I'm trying to build a pyramid, what I'll end up building is something like a stair step effect. But what I'm saying in the lateral surface of this individual track, at least, the finish would be more or less consistent. Whereas for the case of the drop on demand based FDM, even for the same layer, if I am looking in a three-dimensional view, which is very difficult to draw, I'm not sure how. But yeah, say this is one bead which I have deposited, and even here I see that. So the finish is not consistent because of the curvature or the spherical nature of the bead. Thus, even the surface finish would be worse. Will there be interlayer delamination? So there would be pores, of course, but delamination is actually a process-based defect, which also has several other factors controlling it, such as one of the factors which we discussed is the remelting of the previously deposited layer or remelting of the substrate, which will actually control interlayer delamination. And it might be equally bad in both of the cases. So I would suggest this is not generally true. Might happen in certain cases, but yeah, we can't have a general opinion on this. Thus, both A and B, that is both a lack of fusion pores as well as worse surface finish than other conventional AM-based techniques can be expected. Now, this question is asking us to find the exact perimeter of an ellipse with a semi-major axis of length 10 mm and a semi-minor axis of length 6 mm. So we had a formula in the slides where A is the semi-major axis, B is the semi-minor axis, and this parameter lambda is actually equal to the semi-major minus semi-minor by semi-major by plus semi-minor. So if this is my ellipse. This is 2A, this is 2B. Then this is the formula for the perimeter of the ellipse. So would someone like to volunteer and put the values and tell me what is coming out? Of course, it would if you would have been paying attention, you would have noticed that the question is asking for the exact perimeter and no closed form solution actually exists for the exact perimeter of an ellipse. We can only approximate it up to the number of terms of interest using some infinite series, but we would never have the exact perimeter of an ellipse. Thus, without any calculation or without any computation, if you are just paying close attention, we can say that none of the above is a true answer because the exact perimeter cannot be calculated. Again, please, I'm putting emphasis on the word exact here. You can have a reasonably accurate estimate based on the number of the more number of terms that you take in your infinite series, but it will still never be exact. Now, one of the processes which was a slightly unconventional and innovative that was discussed was actually shape deposition modeling or shape deposition manufacturing. And we saw that it was different from the conventional AM process in various ways. And we are asked to choose which are the ways in which it was different. So SDM uses segmentation, whereas AM uses slicing. This is true. And the primary difference is that segmentation can be thought of to be some sort of adaptive slicing only, But the algorithm or the factors which are actually deciding the presence of the decomposition planes are different. So the planes are encountered wherever we encounter a feature which is changing from an overhang to a non-overhang, or a non-overhang to an overhanging type feature, or where we are encountering any undercut, or where there is a change in the material to be deposited. Yes, option A is suitable, yes. SDM uses subtractive operation in every step, whereas classical AM does not. So we saw that in some processes such as the sheet-based additive manufacturing process we discussed last week, it also had an inherent or inbuilt subtractive step. Thus, all sheet type AM processes are inherently of a hybrid nature. However, for most classical AM processes, which are not hybrid but purely additive, there would be no subtractive step. Thus, option is also correct that SDM uses a subtractive operation in every step and sometimes multiple times per segment based on the number of parts it has deposited, whereas classical AM does not. In AM, the support material can support the build material. I mean, it is obvious from the name. The support material is actually used to deposit the build material. Whereas in SDM, both support and build materials can support each other. This is also true, and this was evident in the example that we encountered. Whereas based on the deposition sequence, you can either deposit the build material first, finish it, and then deposit the support material and then finish it, or we can deposit the support first, finish it, and then deposit the build material and finish it as well. So based on the type of feature that we're depositing in that segment, we can deposit them in either order. Thus, all of the above are true. What is the purpose of preheating of build platform in an FDM process? To ensure higher thermal gradient. Now, what is this thermal gradient that we're talking about? So when the material is coming out of the nozzle, it is at some temperature which is like close to or slightly greater than the melting point temperature. Whereas my build plate, so under ambient conditions, would be at some room temperature, which would be say 25 degrees or so. This would be say some 240 degrees, just for a scale. And when this droplet gets deposited into a bead and suddenly encounters this cool surface at ambient temperature, it solidifies rapidly. It solidifies because of the gradient which is existing, say, between, if I look at some intermittent stage, so the temperature of the incoming material, which would be close to the melting point, versus the temperature of the build plate, or even for this first deposited one, the temperature of its upper surface, the curvature which is in contact with air, which is still above the melting point, and the bottom, which is in contact with the build plate, which is at the room temperature. Because of this very high thermal gradient, that is the change in temperature over a very short distance, certain effects will come into the picture, which will actually influence the deposition microstructure, the physical properties, the quality of build, among other things. And a very high thermal gradient is not actually desirable, as the sudden change in temperature can actually have deleterious effects. So we would, of course, not want to increase it or to have a higher thermal gradient. To ensure adhesion of part to build plate. This is true. This is what we discussed. To ensure cohesion of part to build plate. Now, usually your build plate would be maybe made of a metallic material or magnetic material at least, and would also have some coating on top of it to lengthen its life. Cohesion would come into the picture if both the build material and the build plate are of the same material, then cohesive forces would be the dominant ones. However, here we are looking at adhesion because of the dissimilar material, so cohesion is not one of those. And to minimize the power consumption of the liquefier, no, even if we preheat our build plate, still the liquefier would still have to use the same temperature, the same amount of power, which is necessary to melt the filament which is being fed into it. We also looked at based on how the traversal speed is changing or based on how our deposition rate is changing, this heat flux or heat input might need to be further modified. But I mean, even in the least case or in the limiting case, it will still need enough power to actually melt the filament, irrespective of whatever temperature is existing on our build plate. Thus, it does not change or does not alter the power consumption of the liquefier. Thus, option B is the correct one here. Question 8 is asking us which metric is preferable between the centerline average CLA and the root mean square average RQ for reporting surface roughness of a 3D printed part. Remember how in centerline average we say had a profile with asperities. We constructed a line. This line was our constructed, does not exist for real. We can construct it suitably such that the areas above this line, the sum of the areas above equals the sum of the areas below it. Once this line is constructed, I measure the distance of these asperities from this line for a certain sampling length, which need not be equal to the length of the part. It can simply be a subset, and then report my average surface roughness. Whereas the computation for RQ was slightly more involved. It involves the root mean square of these values. But what can be the probable reason for preferring one over the other? So RA is easier to calculate, definitely, but can that really be a reason for reporting our measurements or our measured data? No, it is just a matter of convenience. RQ, as it accounts for the isolated surface features, we also saw this reason in the slides itself, so definitely yes. RQ, as area of two surfaces can be same, but RQ will generally be different if the shape profiles are different. So what is this trying to say? Let us examine. So it is possible that you have three different surfaces which have such profiles. So one can be a sinusoidal, other can be like a square wave, another can be say like half triangle or something, another can be say, full triangles. And it is possible based on, of course, the height from the center line and other factors, the spacing between these features. It is possible that all of these four profiles will have the same RA. When you might have encountered some similar situations in your research or in your studies where you have different types of surfaces which are very different in whatever type of surface feature you see. But even then, the RA value can be the same. So just reporting the RA value with the, of course, the necessary standard deviation and other things does not really capture the essence of the surface. Whereas it is very likely that the RQ will be different. Of course, there might still be cases where even the RQ is the same. But I'm talking about the general case. Mostly the RQ would be different for these surfaces. And which one will have more RQ and which one less, I will not comment on that because it is unwise. I should do not have any numbers here. So it's not so straightforward to actually say, but generally I've encountered that the RQ value will be different, even if the RA value is the same. However, for the purpose of reporting in literature or for articles, I have seen both being used. In fact, RA is the more predominant one. However, if someone is being more careful or if the surfaces are more involved, then they often choose to report RQ. Or you can simply report both of them. That is also good practice. So we see that both B and C are suitable reasons for preferring RQ over RA. So that brings us to the end of this session. So I would be happy to take any questions, should we have them. Okay, if not, thank you for joining in. This was week 7 of the live sessions for Fundamentals of Additive Manufacturing Technologies. I'm Sourav from IIT Bombay and I thank you for joining in. I look forward to seeing you next week. Thanks.
Thank you, sir.
Thanks, Indra.